mentioned, I stated the Teichmüller theorem, and I told you that it comes from his construction using the holomorphic quadratic differential. So let me just review the theorem. So that it's something called Teichmüller's theorem. So we have 2 points in a Teichmüller space of S. So and then what he claimed is that then there is a unique quasi-conformal map, conformal homeomorphism from sigma 1 to sigma 2. What was the symbol? G. So which attains the smallest maximal dilatation among quasi-conformal maps homeomorphisms homotopic to F2, F1 inverse. So there's a unique map having the smallest maximum dilatation in the given homotopic class. So that's the kind of the main thing in the first half of this series of talk. And and then I told you about another theorem, which is actually a part of this theorem, and it's a construction of a Teichmüller map. It's a construction of quasi-conformal map from the holomorphic quadratic differential. So we fix sigma 1 at the Riemann surface and consider phi a holomorphic quadratic differential on sigma 1. Then we can construct a quasi-conformal map F from sigma 1 to some Riemann surface sigma 2, such that the Beltrami or complex dilatation, so that was this one. Also, and the k is a number between 0 and 1, so not including 1. Then there is a quasi-conformal. Then the quasi-conformal homeomorphism from sigma 1 to sigma 2, such that that this is k times this one. And if minimizes the maximal dilatation in its homotopic class. And it's unique. So such in any other QC in the homotopy class, has larger maximal dilatation. So that's the second theorem, which is a part of the proof of this theorem. Okay. So I'm not going to prove this, but let me just show you how this theorem implies that one. Okay. Well, actually, to prove this, you need some kind of the geometry of the quadratic differential, which is an interesting subject, but it takes some time, and probably it will, I thought it would be better to show that how this implies that. And so suppose this is true. Okay. Oh, well, let me just tell you that this sigma 2 and also the map F depend on a given phi and k. So if you choose another holomorphic quadratic differential, then this Riemann surface or this map may change, of course. Actually, there's some kind of injectivity as I show you now. So so for phi, so phi was quadratic differential. So we and probably k. So we have constructed. So we know that there's a map like that. So so this part is probably okay because you can just solve the equation like that, the differential equation, and you have a map. The point is to show that this minimizes the maximum dilatation. But anyway, so we assume that. Then from phi and k, you have a map. Okay, right? So then you have a point in the attachment. So we fix some base point, which is this Riemann surface plus some homomorphism from S to sigma 1. So this is a point in a type-inner space. So this should be the base point. And then from there, so if you're given phi and k, then you have another point in the type-inner space, which is the sigma 2, and the marking, the homomorphism from S is just the composition of this F and the marking of sigma 1. Okay. So then you from this to data, you get a point in a type-inner space. Okay. So now we consider the space of holomorphic quadratic differentials on sigma 1. So it's the definition shows you that it's a linear space, complex linear space. Okay, so if you add two holomorphic quadratic differentials, then you get another holomorphic differential, and you can multiply the holomorphic differential by scalar. Then you get another holomorphic quadratic differential. So it's a complex linear space. Okay, and so and it has a norm. So the norm of this one is nothing but the total integration of this. So if you regard it as a differential form, then if you take the absolute value, it's just some function times volume form or area form. So you can integrate it. So that gives a norm. Okay. So it's a norm complex linear space. Now, we consider the unit ball in this linear space. It's just quadratic holomorphic differential whose norm is unit open ball. So it's whose norm is less than 1, strictly less than 1. Okay. Now, you can define a map from Q1 to Teichmüller space by sending holomorphic quadratic differential phi to a map. So maybe F because F and the sigma 2 depends on K and phi. So maybe it would be better to write it as something like phi K, and so phi K. So we just consider the sigma phi and normal phi, and F phi and normal phi. Okay. So this should be K, and this holomorphic quadratic differential should be used here. Okay, so because the normal phi is uniquely determined by phi, so it's maybe so we can write it as something like this. So then you have a map from the Q1 to the Teichmüller space. And actually, this map is injective. So the first lemma, T is injective. So probably I should prove this. Okay. So suppose you have two distinct quadratic differentials, both of which are contained in Q1. Okay. Okay, right. So and then suppose T phi is equal to T psi. Now then, so you have a solution of this. So you have map F phi from sigma 1 to sigma phi, and F psi which is from sigma 1 to sigma psi. And because the pair sigma phi F phi and sigma psi F psi represent the same point in the Teichmüller space because of this assumption, you have a conformal map, holomorphic map from sigma phi to sigma psi because of that, such that the F phi composed by H is homotopic to F psi. Okay, because they represent the same point. So after the composition of F1 here, they should homotopic. So that we can drop F1 and then you have a homotopy like that. Now, so we should compare the Bertrami or complex dilatation between these two of these two maps. So so because the first so we consider the Bertrami of this one. Bertrami means the complex dilatation, and because this one is by holomorphic map. So if you compare the holomorphic map from the left, then it doesn't change the dilatation. So maybe there is well, yeah. So at least if you take the absolute value, it is the same as this one, because the dilatation doesn't change. So this means and because f psi was the map obtained from the theorem, and the theorem I just erased here, the theorem says this is a unique quasi-conformal map attaining the smallest dilatation. So that means the smallest maximal dilatation. So that means this map should have a norm, essential norm. So this one should have an essential norm. This should be understood as the infinity norm, essential infinity norm. So we ignore the major zero part and just take the supremum. So this should be less than or equal to this one. Okay. Right? But because this one is equal to that one, so that this means sorry, this is psi. So this means this one has norm less than or equal to that one. Okay. This should be norm. And we can repeat the argument exchanging a role of phi and psi. We instead of H, you consider H inverse, then you have a map from sigma psi to sigma phi, and the situation is the same. So you have the inequality of the other direction, so that you have by the same argument. You have inequality in the opposite direction. So this implies their norm are equal. Okay. Right. So now, because the f psi was the unique quasi-conformal map attaining the smallest maximal dilatation, but these two have the same complex dilatation, which implying that they have the same maximal dilatation. So it implies that these two should be the same map. So then the uniqueness part of the theorem implies that theorem is the theorem I erased here. So the uniqueness part implies this should be equal. Okay. Right. So then again, you have the this is just the composition of the holomorphic map. So the complexization are the same. So the complexization of the phi and the complexization of psi should be equal almost everywhere. So what was the complexization of phi? That was by definition that was the something like this. And this equality means this is equal to the same kind of the function for psi. Okay. So then look at the norms of these two. So these are norm 1 because it's just same function. This is just the complex conjugate, and this is just the absolute value. So this part has absolute value 1. So this implies that norm of that and norm of that are equal. Okay? Right? Then you can divide these two by this norm. Then what you get is this is equal to this one. Almost everywhere. So I taking the complex conjugate, then this implies phi should be some constant, or maybe it's a bit so there's a bit cheating because this constant may, so it looks like this constant may depend on psi, but anyway, so this actually implies phi is equal to psi almost everywhere, but because they are holomorphic, they're everywhere. And except for the constant terms. Right. And then, okay. And then so because these constants must be 1, because we have this inequality. So this implies phi is equal to psi. Okay. So here this step is not so trivial, but you use the fact that they are the holomorphic function, and but anyway, so it's just exercise of complex analysis. Right. Okay, so that means that implies that T is injective, and well, maybe I don't have enough. So the next lemma is something like that. So T is proper, meaning that the inverse image of compact set in the Teichmüller space is compact. So this part is again needs some argument, but this is easier. So I'd like to leave it as an exercise. So it's the argument should be by contradiction. So you suppose that there is a sequence of the holomorphic quadratic differential which converges to some point such that the image by T diverges to infinity, then you get a contradiction. So by taking the limit in the holomorphic quadratic differential, because in the space of holomorphic quadratic differential is just kind of that you can take the limit holomorphic quadratic differential, and you can consider the image of by T, and so you should show that actually that should converge to the point or something like that. So that it's not so complicated, but you need to use some argument because the definition of T is not so straightforward. So that you have to use the fact that the 2 point, if it converges to something, then that should converge to the image of that point or something like that. For that part, you need some kind of argument. But anyway, so this is a kind of exercise. So you have and also the continuity is can be shown in the same. So T is continuous, proper, so proper continuous, and the injective. Okay. Now we know the topological type of the Q1. Since this is the space of some kind of differential forms, and here you need to use the Riemann-Roch theorem, and then you can show that it's just a linear space of the dimension 3G minus 3. So that was a linear space, and complex linear space, and you can compute the dimension using Riemann-Roch theorem. And on the other hand, so this is a unit, open unit ball inside that. So it should be homeomorphic to the Euclidean space of dimension 6G minus 6. Okay. Yeah. It's just a topological. Topologically, it's the 6G minus 6 dimensional Euclidean space. And on the other hand, we know that topological type of the Teichmüller space. So I didn't show that I just mentioned that it's a homeomorphic to the Euclidean space of the dimension 6G minus 6. So they are the same Euclidean space. So the Euclidean space is having the same dimension. And you have a continuous injective proper map. Then it's just an exercise that should show that then T must be homeomorphism. In particular, it is surjective. So the surjectivity means for any given point in the Teichmüller space, you have a Teichmüller map from the sigma 1. So it's just a statement of the theorem for the existence of the Teichmüller map. So by this kind of argument, you can show that the theorem, the second theorem implies the first theorem. So after yesterday's talk, so some students came to me to ask the good reference for the Teichmüller theory. And let me just mention one book. So That's written by Imayoshi and Taniguchi. Oops. Two Japanese mathematicians. And the title of the book is An Introduction to Taichimura spaces. So it's published by Springer in 1992. So I have checked the list of the Springer website yesterday evening. Then I found that you can just still have it. So you can buy it. And in particular, they have an ebook. So if your university happen to be a subscriber of the Springer link or something like that, the Springer ebook project, then there's a chance that you can download it from your university site. So it depends on which institute you are from. But I haven't checked that it can be downloaded here or not. But anyway, so that can be also bought as an ebook. Okay. So so this was just kind of the review and some more precise explanation of the two theorems I talked about yesterday. So let me turn to a new subject. So that now what I'd like to talk about is something called the Roydens theorem. And for that, I need to, so it's a mapping class by action. Actions on Taichimura spaces. Especially Roydens. So let me define mapping class group first. Only contain short ones. Okay, anyway, so let S be a closed surface, closed oriented surface. Of genus greater than or equal to 2 as before. Then we consider mapping class group. So that stands for mapping class group of S, which is defined to be the set of the auto-homeomorphisms. That is a homeomorphism from S to S. And we identify two homeomorphisms which are isotopic. So as I said yesterday, this is the same as homotopic. So if two homeomorphisms are homotopic, then they are isotopic also. Okay, so then it has a group structure. So if you have two homeomorphism, F1 and F2, then you can compose them and get a new homeomorphism from S to S. So this is the binary operation. And so identity, so is just the identity of the identity map, identity homeomorphism. And the inverse is just the inverse as a map. So, and this structure induces the group structure on the mapping class group. Okay. Right? So there are many things known about this mapping class group, but still it remains mysterious. So for instance, it's known that this group is finitely generated. And actually the concrete system of the generators was given. And also that there's it's known that it's finitely presented. And you have a concrete system of the relators. Still, it's very difficult to understand the structure of this group. So that there are still many works going on now on this mysterious group. One of the good things to study tachymeral space is you can also you can consider the action of the mapping class group on the tachymeral space, and that if we understand the action very well, then you can understand. So it's the mapping class group. So that's one of the tools to understand the mapping class group, the tachymeral space is. So now let me define the action of the tachymeral space. So so you have a you have a point in a tachymeral space. The point in a tachymeral space was a pair of Riemann surface and homeomorphism from S to that Riemann surface. And take some element in the mapping class group. So mapping that should be represented by a homeomorphism. So maybe it's better to write it that way. And then gamma is a homeomorphism from S to S. Then we define the gamma of RF. So the action is the same Riemann surface, but changing the marking. That is the homeomorphism from S to that Riemann surface by composing the inverse of gamma. So by defining gamma like that, then you have action of the mapping class group on TS from the left. And actually, this action is isometric with respect to the tachymeral metric. So that this should be the theorem. This acts. Oh, yeah.
How we can say that gamma is bijective?
Gamma is a homeomorphism. So bijective, it's a homeomorphism. So it's the inverse is also a homeomorphism. So gamma was an element of mapping class group. So the each element of mapping class group is represented by a homeomorphism from S to S. So it has inverse. Inverse is also homeomorphism. So the mapping class group acts on tachymeral space by isometries. well-definedness. Well-definedness. Okay. What do you mean by well-definedness? So, okay. So so if you have another representative of gamma, then you have a gamma inverse, another gamma inverse here, but they are homotopic. So you have two markings which are homotopic to each other. So it gives the same point in the Teichmüller space. Is it what you're asking? Right? Okay. So what matters is the homotopy class of that one, because this is just marking. So if the homotopy class doesn't change by the changing the representative, then that's okay. Now, so I'd like to show that this is actually isometry. So suppose you have two points in the Teichmüller space. Oops. Oh, I usually use something like sigma 1. I'm not sure why I changed it to R here. Anyway, so anyway, so that can be sigma 1 or anything else. But anyway, so so suppose you have 2 points, then the distance between these 2 points was defined to be the smallest, half of the log of the smallest dilatation. So suppose you have a quasi-conformal map with maybe K quasi-conformal map in general. Then so between these 2 points obtained by the just making gamma act on them, something like that, then H R1 to R2 is homotopic to the this one. So if you consider the inverse of that one, you have a gamma composed by F1 inverse. So that is equal to the F2. Okay. So because that was that should be in the homotopy class of that. So F should be okay. Then this should be homotopic to that. So this gives K QC between these 2 points. So if you consider the infimum of the half of the log of this one, then you have the infimum of the half of the log of this one. So that they have the same distance. So these 2 points and these 2 points have the same distance. So that's the end of the proof. So you have an isometric action at the mapping cross group. So but what's interesting is that you have a kind of the classification of elements of the mapping cross group using the Teichmüller space. So, but it's so I have 15 minutes. So maybe I should talk about it later. And let me just turn to the Royden theorem before that. So here's the theorem. Oops. By Royden. Oh. So he showed that the entire isometric group of the TS with respect, to the Teichmüller metric is equal to the mapping class group. Probably I should say that it's kind of the orientation preserving or the extended mapping class group. So and there's some subtlety here because I didn't say. So what I wrote here, what I defined when I defined the mapping class group, I didn't say anything about the orientation. So usually when we define the mapping class group, they just consider the orientation preserving homeomorphisms. But we also need to consider the orientation reversing homeomorphism. So then, maybe it's better to write it. Probably when I put star here, that means orientation preserving. Orientation preserving homeomorphisms. So that's an index 2 subgroup of the mapping class group. Okay. So actually, this theorem comes from the following infinitesimal version of the mapping class group. So I will show you the stronger version of this theorem, and I don't have enough time to explain the proof. So, but maybe tomorrow I will, if I have enough time, then I'd like to also show you how to prove that, or just sketch how to prove that. So anyway, so we have a kind of the stronger version of this theorem. So is it clear that the statement of this theorem? This is the isometry group. So this is the group of the isometries TS with respect to that one. That again makes a group. And that as a group, that they are the same. They are the same. So the action of mapping class group on that is just a group of isometries on that. Probably orientation preserving. So and that theorem is a kind of corollary of the stronger version. So to state the stronger version, let me just recall you that you have you have a Beltrami or complex that. So you have a if you have a holomorphic differential, holomorphic quadratic differential, then from that you consider something like that to construct the complex dilatation like that, construct the Teichmüller map. So although I didn't tell you this, but actually, so if you make k changes, so if you just make k vary, then you get the kind of the arc in the Teichmüller space. So you can change it from 0 to 1. For 1, there's no point. So that from 0, so in a half open interval, then it gives a arc in the Teichmüller space. So, but with appropriate parameterization, this arc is a geodesic in the Teichmüller space. So this gives changing k. So the parameter should be something like probably something like I don't remember where the no. So 1 minus e to t and e to t plus 1. So k, if you parameterize k by using such a function, so if t is 0, then it's 0, and as t goes to infinity, oh sorry, it's the other way. So if t goes to infinity, then it approaches 1, right? So when t goes to 0, it's a 0, right? So by this parameterization, and you get the map from the 0 infinity to the Teichmüller space, so fix phi. Then actually this is geodesic. So geodesic means so the geodesic in a metric space. So this parameter gives distance between any 2 points on that line. Okay. So this means that this kind of Beltrami gives a tangent vector on the point, the starting point. So this becomes a tangent vector. So if we change phi, then you have a different direction, and so if as k goes to 0, you have a derivative, and that gives the derivative should be this one. So that is a kind of tangent vector. That can be regarded as a tangent vector. And for another holomorphic differential on the sigma, you can consider the integral of the product of the complex dilatation like that and the psi. So that shows that this space can be identified with the cotangent bundle, or with the cotangent space, sorry, because I fixed the point sigma, so it's a cotangent space of Teichmüller space at sigma f. So now, the stronger version of that theorem is as follows. So I can state the theorem. This is a stronger Roydens theorem. So suppose you have a map from the quadratic differentials, the space of quadratic differentials, and to another quadratic. So sigma 1 and sigma 2 Riemann surface is homeomorphic to S. So that suppose you have a map from the quadratic differential of sigma 1 and to the quadratic differential of sigma 2, which is linear, complex linear, and the preserves norms. Then there exists there exists map from there exists a bihomomorphic map from sigma 2 to sigma 1 such that K of for any phi in QH of sigma 1, K of phi is equal to the pullback of phi by H. So if you have a quadratic differential here, then you can consider the pullback of that by using this homomorphic map. Okay. So this means if you have so you just look at the cotangent spaces at the 2 points in the Teichmüller space. And if there is a linear isometry between these 2 cotangent spaces, then it should come from homeomorphism by homomorphic map between these 2 Riemann surfaces. So the cotangent space determines the structure of the Riemann surface. So that's what it says. And actually, this is kind of an infinitesimal version of this theorem. So I will show you how this implies that, or how to prove that tomorrow. Okay, so it's time to stop now. Okay, thank you very much.